I would like to demonstrate the Hartnell governor equipment and experiment setup. So this is Hartnell governor. Here these two are bell crank levers. So these two are balls of mass 0.45 kg. So this is denoted by small m. So this arm is called as vertical arm or ball arm of length 75 mm denoted by X. So this is horizontal arm or roller arm of length 95 mm denoted by Y. So this is frame. So this is a spring. Here we see this is the spindle. Here this is the collar. This is the sleeve. Here we see a graduated scale to measure the sleeve displacement. Okay, here these two bell crank levers connected to the frame at these 2 points. Here a spring is, we keep it on the spindle, governor spindle, and we mount a frame on, and with the help of nut we tighten it. Okay, here to run the governor spindle we need a DC motor. So this is the DC motor. Okay, this DC motor is connected to the Hartnell governor spindle with the help of V belt drive. So that is under this frame. Here by using the speed control unit, so we connect this to the DC motor. So we plug it, and we by varying this regulator we vary the speed of the DC motor and simultaneously vary the speed of the governor spindle. Here at these two fly balls, a centrifugal force Fc is acting, which tries to move away this bell crank lever moves away from the spindle. Okay, here there is a spring force is acting downward, which controls and balance this centrifugal force. Here, just by giving the power and by varying, so we note down the sleeve displacement. It is moving like this. Note down the sleeve displacement, that is denoted by H. Units are mm, and corresponding speed with the help of contact type tachometer by keeping here. So that is we note down here in the speed column, the units are revolutions per minute RPM denoted by N. So this is about our Hartnell governor setup. So it is called as a spring loaded governor. So because we are using spring here to control to balance this, that is the reason we call it as a spring controlled governor. Now I am explaining the observation table and procedure how to do this experiment. Okay, this is the observation table. Here we see we have two tables. Let me explain the first table. Serial number, speed. Anyway, we note on the speed corresponding sleeve displacement from the experiment. Note down here and here. So here we see the radius of rotation, small r, units meter, and there is a controlling force F, units are Newton. Okay, here we see already explained that is vertical length of bell crank lever that of X 75 mm and horizontal length of bell crank lever Y 95 mm. So we know mass of the ball m equal to 0.45 kg. So initial radius of rotation R naught equal to 132.5 mm. So that is from axis of the spindle to here. So from here to here. So from here to here, that is R naught when it is in equilibrium position. So that is of 132.5 mm. So to calculate the radius of rotation at different speeds and corresponding sleeve displacements, we have a formula. So that is R equal to R naught plus H into X by Y. Anyway, we know the R naught, that is radius of rotation of 132.5 mm. So H, that is sleeve displacement. From here we get that value. So X and Y, that is vertical arm length, that is 75 mm X, Y is 95 mm. So from these values we get the radius of rotation for corresponding reading. So now coming to the controlling force. So to calculate the controlling force, the formula is spring stiffness small s into sleeve displacement. Yeah. So now I will explain how to calculate the spring stiffness value. So from the experiment, just we note down 4 readings. We do the same experiment 4 times. That is at 4 displacements, you note down the 4 speed values. So note down 2 values from these 4 values, and here you note down those 2 values. So speed, calculate the corresponding angular speed. So formula to calculate the angular speed, that is omega equal to 2 pi n by 60, units are radian per second. Then corresponding sleeve displacement and corresponding radius of rotation. Note down all this. Okay. So then in the same way, so then we calculate the centrifugal force Fc. Units are newtons. We know the formula for centrifugal force, that is Fc equal to m omega square r. Here m already we know, that is mass of the ball, 0.45 kg. Omega we get from this omega value. Smaller radius of rotation already we get from here. So then we get Fc, centrifugal force value. So then next, from second reading speed, calculate corresponding angular speed omega just by using 2 pi n by 60. Anyway, we know corresponding sleeve displacement also and corresponding radius of rotation, which is we get from this above table, and calculate the centrifugal force. Okay, here this for first reading we get the centrifugal force, that is Fc1. For second reading, the centrifugal force, that is denoted by Fc2. Calculate the centrifugal force m omega 2 square r2. So then we get Fc1 and Fc2 for those 2 readings. After getting those centrifugal forces for those 2 readings, so simply substitute here in this formula. This is the formula to calculate the spring stiffness. S equal to 2 of Fc2 minus Fc1 by R2 minus R1 into X by Y whole square. We know already Fc1 and Fc2 here. From this, R1 and R2 corresponding radius of rotation for first reading, the radius of rotation is R1. For second reading, radius of rotation is R2. So substitute all the values, we get the spring stiffness. Substitute the spring stiffness value in Newton per mm here. After getting the spring stiffness, calculate the controlling force by substituting spring stiffness, that is multiply that spring stiffness into corresponding sleeve displacement, we get the controlling forces for the 4 readings. After getting all these values, so need to draw the graphs, that is speed versus sleeve displacement. So then radius of rotation versus controlling force.